Okay, in our next example here, we have 100 students were surveyed and they were asked what their favorite brand of drink was. 20 students' favorite was water. I select 40 students at random and count how many drink water. We want to determine the probability that 5 people drink water, 3 people drink water, 30 don't drink water, and on average, how many of the 40 would you expect to drink water? All right, anyway, looking at this problem here, identification. I'm counting how many are doing something, right? Correct? I'm counting how many are doing something. There's two things that can happen here. They either drink water or they don't drink water, right? So the first thing I'm going to do is I'm going to state what I'm counting. The number that drink water. Got it? How many possible number can there be? Up to 40. There are 40 people that were surveyed. The probability of them drinking water comes from the 100 students that were surveyed and 20 were found to drink water. So 20 out of 100, which is 0.2. Q is the opposite. So that's 0.8. They have to add up to 1, right? So here are the 4 basic pieces of information once we identify this as being a binomial distribution. We're counting how many are doing something. There's one of two things that can be done. They either drink water or they don't drink water. We found out how many possible how many trials there were, 40. The probability of success, drinking water, probability of failure, not drinking water. So the first question is the probability x is equal to 5. Well, we have the formula. C of 40. Gotta stop pressing that button. C of 40. Pick 5 times the probability of what we're counting, 0.2, supposed to be a 0, raised to how many? 5. Probability of failure, 0.8. Well, how many would not be drinking water? 35. Okay, you can go through the calculations, but each one of these is equal to the following. C of 40 pick 5 is 658,000. 8.2 to the 5th is 0.0032. Hold on. Alright, so 0.8 to the 35th power. And this is where you do have to be careful about rounding, because some of these numbers can be very small. And when these numbers right here are very small and these are very, very large, the probability could turn out to be something other than 0. So again, you should keep at least 4 places, but sometimes that's not even enough. Especially when for some of these types of problems, which on a test I'm gonna make sure that doesn't happen. But anyway, when you multiply all this together, you're gonna get this is equal to 0.085. Okay, so here's the formula for calculating the probability of a binomial distribution. We're asked if it equals something. The next one, the probability x is equal to 3. Once again, we take out the formula. C, there's 40 trials. I want 3 successes. The probability of success is 0.2. How many successes? 3. The probability of failure is 0.8. How many failures? Well, there's a total of 40. Take away the 3 that were success, so 37 failures, right? So these two exponents have to add up to the number of trials, right? When you do the math, this is going to be 9,880. 0.2 to the third power is 0.008. 0.8 to the 37th power is 0.00026. When you multiply all that together, you get 0.021. Okay, and there's the one above that, right? All right. Now, the next question. The probability that they don't drink water. Remember, we're counting how many drink water. So either we're going to have to change what we're counting and change all of this over here, okay? Or we need to change the statement itself. Well, if 30 don't drink water, that's the same thing as 10 do drink water, correct? Got it? 30 don't drink water, there's 40 people, so that's the same thing as asking the question that 10 do drink water. Well, get out the formula. That is C of 40 pick 10 times the probability of what we're counting. How many? 10. Probability of what we're not counting. How many? 30. Now I'm doing this problem to point out something that I just said a little while ago. I'm going to show you these numbers. These numbers are pretty big. C of 40 pick 10 is 847,660,528. A very large number. 0.2 to the 10th power is a very, very small number. 0.8 to the 30th power is 0.00124. So again, if you rounded this to 4 places, your answer would be 0. Okay? Your answer would be 0. Now, when I do the actual calculation, it comes out to be 0.1075. Almost a 10% chance. That's why you do have to be careful when you do round, okay? That sometimes very large numbers mixed with very small numbers can result in something in between, right? Okay, so last question on this one. On average, how many of the 40 workers would you expect to drink water? Well, we know how to calculate the mean. The mean for binomial is n times p. In this problem here, n is equal to 40. P is equal to 0.2. That is equal to 8. So we expect 8 of the 40 to drink water. Moving on to the next problem. Okay, so once again, you should be trying these problems out and then watching the video. Okay? All right, so our next question. At the old colorful light bulb factory down on the river, the percentage of blue light bulbs is 10%. Packaging of light bulbs is a random process. If you pick up a box of 100 light bulbs, determine the following. The probability you get exactly 3. The probability you get at most 8. So once again, we're counting. We're counting how many blue ones. Well, either you get a blue one or you don't get a blue one. So if we let x equal to the number of blue, then x has a binomial distribution. The number of trials is equal to 100. The probability of getting a blue one is 0.1. The probability you don't get a blue one is 0.9. So here's our key information right here. The mean and standard deviation are also key information, but we're going to work with that later on. Okay? All right, so the probability you get exactly 3 blue bulbs, that is, the probability x is equal to 3, once again, is given by our formula. C of 100, pick 3, times probability of what we're counting, 0.1, how many? 3 blue ones, times the probability of what we don't want, 0.9. Out of 100, we got 3 blue, so there are 97 that are not blue. When you do your math, this comes out to be 161,700. Gotta get used to running my zeros as zeros, right? Probability of 0.1 to the 3rd power is 0.001. probability of 0.9 to the 97th power, 0.0000036, right? And you do your math, 0.00589. I gotta get used to this pen still. Takes a while, long while. But anyway, that's the answer to this one. Now for the second one, we want the probability at most 8 are blue. Well, at most 8 are blue is no different than getting 0 blue ones, 1 blue one, 2 blue ones, 3 blue ones, all the way up to 8 blue ones. Now in this chapter here, in this particular chapter before normal distribution, you have to keep in mind that there is a way of calculating this, but this is a mess. We have to apply this formula 1, 2, 3, 4, 9 times. Well, that's what you got to do. That's what you got to do. But I told you for my students, okay, so this is for other people, okay, but for you, my personal students, I told you there's a better way. And if we have an inequality associated with the binominal, and it's not reasonable, meaning 1 or 2 uses of that formula, I already told you you can go to the normal approximation, right? All right, so that's where we're going now, the normal approximation. You should be familiar with the standard normal distribution and how we get to the standard normal table, right? Subtract the mean, divide by the standard deviation. This is called a z-score. So if you're not familiar with this, then you should stop the video now, come back to this after you go over and study the basic understanding of the normal distribution and the standard normal distribution, and then return. So when you're working with the binominal distribution, if it's the case that the product of n times p is at least 10 or more than 10, you can use the normal approximation as a reasonable estimate. Well, that's going to be the case for us. In fact, I already told you, if you have an inequality associated with the binominal and you have to perform that formula more than 2 times, I'm saying that's for me, I will say just go to the normal approximation, okay? All right, we're just going to go to it. So you really are supposed to check this condition here. Now, there will be an adjustment to be made. It's called a continuity correction. That is, we're going to be adding or subtracting a half to our inequalities. We're going to either have to add or subtract a half to our inequalities. That is because we're going from a discrete distribution to a continuous distribution. All right, so now we're going to take a second look at our problem up here. And we're going to use the normal approximation to figure this probability out. All right, so now what are we looking for? We're looking for the probability that x is less than or equal to 8. So I'm going to draw a little number line over here. Here's 8, and we want to be less than or equal to 8, right? Just to draw a big circle, right? So I'm either going to add a half to 8 or subtract a half to 8. Notice if I subtract a half, I will not be including 8, but we want to include it. So that means I'm going to have to go above 8, 1/2 unit, and convert 8 to 8.5. In other words, I'm going to figure this one out. The probability that x is less than or equal to 8.5. So we made this, quote, continuity adjustment. This is going to take us now to the normal table. How do we get to the normal table? We subtract the mean, divide by the standard deviation. Now, remember, the mean is n times p. If you do your calculations, go back above, look at the problem. The mean is equal to 10. The standard deviation is the square root of npq. If you go do your math from above, multiply npq, take the square root, you're going to get 3. So we get now to the table, and we have the probability that z is less than or equal to 8.5 minus the mean divided by the standard deviation. When you do your math, that's the probability of z being less than or equal to negative 0.5. I am assuming you know how to work with the table now. So the answer to this problem is 0.3085. Moving on to the next problem. I'm really kind of pressed for a little bit of time. Well, we only have 2 more. Okay, so we're just going to extend this video out. It's probably 20 minutes. All right, assuming, again, x is the number of blue bulbs, we want the probability x is between 5 and 15. So I'm going to go over here, draw myself a number line, 5, 15. Now, for this problem here, I want to include 5, but I don't want to include 15, right? Look right here. So if I'm going to include 5 and I don't want to include 15, I'm going to have to go below 15. So I'm going to have to go to 14.5. But if I want to include the 5, I'm going to also have to go below 5 and go to 4.5. Remember, this is what I'm looking for. I'm looking for this interval here, right? If I want to include 5 in this particular interval, I'm going to have to subtract a half from 5. If I don't want to include 15, I'm going to have to subtract a half from 15. So my interval is now going to be the probability that x is between 4.5 and 14.5. My next step is to get to the table. I get to the table by subtracting the mean, dividing by the standard deviation. Subtracting the mean, dividing by the standard deviation. Get the old calculator out. This is the probability of being between minus 1.83 and 1.53. This is the second scenario. The larger percentage minus the smaller percentage, right? When you do your math, 0.8996, which is about 90%, right? All right, the last one, the probability I get more than 12 blue bulbs, more than. Looking at my number line, I have to be above 12. I'm going to just do it this way. Sometimes we get a little too fancy with the colors, right? But I don't want to include the 12. I want more than 12, right? So if I don't want to include 12, I'm going to have to go up to 12.5. So I'm going to replace this with the probability of x being greater than 12.5. I get to the normal table by subtracting the mean, divided by the standard deviation. I do my calculation, 0.83. This is the third scenario, the opposite of the table. So subtract from 1, what I found in the table. I do my math. I get 0.203. And there you go. I'll erase that. I got less than 20 seconds. I'll rewrite that, 0.203. And I am done. So again, good luck with this. You can rewind the video and check your answers out. I'll kind of go backwards and show you all the answers again. My suggestion is working the problems out and then comparing. That's it. All right, well, good luck.